Hi, this is lesson 2.3, continuity. We're going to be looking at continuity at points, continuous functions, some algebraic combinations, composite functions, and the intermediate value theorem for continuous functions. So basically we're just looking at what's a continuous function, what's not a continuous function, what's it mean to have continuity, or the different types of continuity we can have. First thing I want you to try is to find the points on the graph where this function is continuous. So not where it's discontinuous, but where is this function continuous. So hit pause. Okay, hopefully you said something like, well, this function is continuous along the domain of -2 to 10. Okay, those brackets mean you're including -2 and 10. I know the -2 doesn't have a dot, but it doesn't have an open circle, so you consider it to be a dot there. Except for the points, well, 1, it's a filled in dot, so that's still continuous. 4, though, it breaks there at 4. So except at x equals 4, and then also at 5, and x equals 5. Those are the two places that it's not continuous. Okay. Here's the definition. Continuity at a point. Interior points, the limit of f of x as x goes to whatever that point is, they call it c, is equal to the value of f of c. So remember to have the limit from the left equals limit from the right equals that specific value at c, is kind of what that top one says. Endpoints, though, at an endpoint, kind of like on the previous one, we were saying that it was continuous to that point, that -2. So that would be from the right. So that would be like this first definition. The limit of f of x as x goes to a from the right is equal to f of a, or all the way to the right on the last graph would be, we're coming in from the left side. So if we're looking at that 10 value, it would be defined as continuous with the limit of f of x as x goes to b from the left equals f of b. So that kind of is that. It would be limit of f as x goes to 10 from the left is equal to f of 10. Okay, next. I want you right now to hit pause and match. I know there's only 3 graphs and there's 4, so you're going to have 1 left over. Match the graphs with the correct type of discontinuity. Hit pause. Alright, hopefully you saw that this first graph was an infinite discontinuity, because this graph goes down to -infinity, then it jumps, or it discontinues up to positive infinity, and then comes back down. So this one would be part C. The next graph, you can see it goes up, 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 and then that little point looks like it's removed and drugged down in this case. It doesn't even have to be drugged down. Sometimes you'll just have one with an open hole there, and you won't have anything down here. But then it starts back up again. That would be A for a removable discontinuity. Okay, it looks like they just removed that point and put it down below. And then the third graph, just those 2 lines, it goes from the left up to that point, and then it jumps up to the next line up there. So that would be the B jump discontinuity. Now your book does show an oscillating discontinuity. It would kind of look like a graph that went, I don't know, up like this, and then kind of goes closer and closer, and then stops. And then on the other side, it kind of continues the same mirror image over, something like that. Because it does stop in that, I guess they call that oscillating discontinuity, but it's not very common, so we'll pretty much focus on removable, jump, and infinite discontinuities. I want you to hit pause here and do this exploration. I think it's really good, and I think it'll give you a good understanding of some concepts of discontinuity. So work through this. The only thing that I'll go over is number 4. So if you have more questions beyond 4, please bring those in. But the only thing I'm going to go over. So go ahead and hit pause. I will go over 4 after you're done working on this. Or if you get up to a point where you're stuck on 4, go ahead to the next slide and or hit play or whatever. I think it's YouTube. So hit play and you can see the next part. And then just rewind to get back to C5. So go ahead and hit pause and work on this for me, please. Okay, hopefully you did all right up to 4. For 4, I had to use polynomial division to divide out in x minus 3 from the numerator of that function. The numerator was x cubed minus 7x minus 6, and I factored out the x minus 3 to get the x squared plus 3x plus 2. So now the numerator simplified to this, or I don't know, expanded, I guess, up to this form here. The denominator I factored and it went to this form here, which allowed me to cancel out the factors of x minus 3 to give us a simpler function here. Now, it's not the same function, but it's pretty darn close. Okay, so if you were to graph this function, it's going to look a lot like this function here. The difference is you can't just get rid of these because it does have a hole at 3, because you can't divide by 3 really. So the original equation, you know, you can't just go to this and say it's the same thing. It's not, but it will give us what the limit is at that point. It will show us where the limit is as you approach 3. So let's use this simplified version, okay, to find the limit. Remember, when you're finding a limit of a specific value versus going to infinity, we can just substitute first. If you can substitute and you don't get that you're dividing by 0 or some crazy number that you can't do, then it should work. Here I can see we're going to divide by 6, so we should be good. So it's going to be 3 squared plus 3 times 3 plus 2 over 3 plus 3, which is equal to, that's 9 plus 6 is 15 plus 2 is 17 over 6. Okay, that's what this function approaches as you go to 3. So that's the limit as x goes to 3. Okay, if you haven't already, continue on to number 5 on the exploration, number 1 there. So go back, and then you can skip ahead to the next part. Okay, you're doing really well. I'm hoping at home you're doing really well. This is kind of starting to make sense, so I want to try to challenge you a little. I want you to tell me, is this a continuous function? Is the function of f here on the right, is it a continuous function? So hit pause, write something down, yes or no, this is continuous. Okay. This function is a continuous function. And I bet a bunch of you are kind of going, well, no, it's not, because we already talked about this has infinite discontinuity. That's true. It does. Oh, hold on one sec. Sorry about that. Sometimes the phone rings. Anyway, we've got this function, and yes, it is a continuous function. Yes, there is discontinuity in the function, but here's the deal. If there's discontinuity anywhere along the domain of a function, it can still be a continuous function. Yes, this thing is discontinuous at 0. It goes to infinity. Both sides go to infinity at 0. But the domain of this function is all real numbers except for at 0. Okay, so because it's continuous along its domain, it is a continuous function. So just be real careful here. It is not this graph is not continuous on the interval at 0, but the function is continuous because it's continuous along its whole domain. Okay, kind of a weird thing there. So to test you a little bit, think about this. Is the function from exploration 1, the thing that you did 2 slides ago, is that a continuous function? Hit pause, write down your answer. Okay, hopefully you said that yes, that function, even though it has discontinuity in it, that the function is continuous because, like we said before when we factored that x minus 3 out, saying that that domain of that function is all real numbers except for at 3 and negative 3. But it's continuous along all the other numbers. So since the domain is all real numbers except for 3 and negative 3, and those are the same places where it's discontinuous, but it's continuous along everywhere else, that this function is a continuous function. Okay, so the last question on here is the greatest integer function, in other words a step function, is the greatest integer function continuous? Hit pause and write down your answer. Okay, well, the greatest integer function, the domain of the greatest integer function is all real numbers. Okay, there's nowhere in there, every number on the greatest integer function has a value. Okay, but there are places that are discontinuous on the greatest integer function. So the greatest integer function is not continuous because along its whole domain there are points of discontinuity. So hopefully you can kind of see the difference between the two there. Okay, here's some properties. If f and g are continuous, then if you were to put the functions together and say we were doing this at C and doing this at C, so let's say we were doing f at C and then we add on another function of g at C, those will still be continuous. If we subtract them, they're continuous still. If you multiply them, they're continuous at C. If a constant is multiplied by the function, it's still continuous at C, or if you divide them, as long as the denominator is not equal to 0, it is also continuous. Okay, so you'll use that a little bit when you're working on some problems, and you'll also, this one will be the bigger one, composite functions. So f is continuous at, if f is continuous at C and g is continuous at f of C, then it makes sense that the composite function g of f is continuous at C. So hopefully that kind of makes some sense for you. It's kind of, I don't want to say it's common sense, but it does make sense. Okay, the intermediate value theorem for continuous functions. Basically, if you have a continuous function from point A to point B, and C is a point in between, then somewhere along there, if you're going from f of A, your outputs are going from f of A to f of B, then somewhere along there you fall in the middle along that path between f of A and f of B. It has to. That y naught, what it shows in this graph here, you have to reach it at some point. That's what happens with the continuous function. It never jumps, you never skip anything. A continuous function, or if it's continuous along this interval, then you hit that somewhere. It would be like saying if you drove all over town and the furthest distance you went away from your house was 20 miles, well, somewhere along there you were 10 miles away from your house because, 10 is between 0 and 20. So that's basically a simple way of kind of thinking of this. Again, I don't want to say it's common sense, but it makes sense when you think about it. Okay, that's the end of this video. Bring any questions that you guys have into class, and I hope you have a great rest of your night or afternoon or morning or whenever you're watching this video. Thanks.